Okay, since radial moment, there is a negative radial moment at the edge. Okay, MRE, that is a negative value. So we have to provide radial negative reinforcement at the edge. So radial distance from the face of the support up to which reinforcement will be provided. That is from the greater value of the following conditions. That is 1, 2 and 4. So from these three conditions, okay, first condition is distance of point of inflection from the edge plus D. So we are providing radial reinforcement. Now we have to know at what distance from the edge, at what distance this radial reinforcement is to be provided in order to overcome the negative radial moment at the edges. Okay, we have to know the distance. So first condition is distance of point of inflection from the edge plus D. What is point of inflection? That is the point at which moment changes its sign. We have already calculated that distance, that is a minus radius minus a by root 3. It is also explained from the figure of moment distribution. Figure also we have explained that. Uh, First condition is that, and second condition is distance of point of inflection from the edge plus 12 phi, and the third condition, fourth condition is LD is equal to phi sigma st by 4 tau BD, that is equal to this value. So we have already find that LD value 47 phi in the previous case also. For your information, I am explaining this also. Tau BD in case of HYSD bars, in case of not in case of plain bars, in case of deformed bars, we have to increase the bond stress, that is tau BD given in IS code by 60 percentage. That condition is given in the development length provision in IS code. That is 1.2 is the bond stress in case of M20 concrete, that is given in the table. So 60 percentage of that 1.2, we can get the value of tau BD for HYSD bar using M20 concrete 1.92. You can refer it from close 26.2.1, that condition. We will get 47.5. So LD is 470 mm. So this condition, fourth condition and first condition and second condition, from all of these, the greater value is the distance of radial reinforcement from the edge. So 1398 mm is the largest one. So we can provide 1400 mm as radial reinforcement distance. So we have the available depth D is equal to 130 mm. Okay, that is my minimizing that value from the total depth D minus 15 minus 5, half of the dia. So AST is equal to 0.5 into 20 divided by 415. So substituting that value, we are substituting the value of moment, negative moment, taking only the magnitude. Then AST we will get as 288. And spacing using 10 mm bars, spacing we will get like this, 272.145 mm. So provide all bars 10 mm bars at 270 mm spacing and up to 1400 mm distance, and code specifies that at least 1/3 of the total negative moment reinforcement at the support, that is this reinforcement, total negative moment reinforcement, radial reinforcement, and its one third value shall extend beyond the point of inflection for a distance not less than 1 by 16th into clear span. So this is provided in the clause 26.2.3.4. You please go through that clause. You will understand that the reinforcement should be extended. At least 1/3 of the reinforcement, negative reinforcement, should be extended from the point of inflection to a distance not less than 1/16 into clear span. That is, we have already calculated that in this third case, that is distance of point of inflection from the edge plus L effective by 16. 6000 is the effective length, that is our dia. Okay, we will get it as 1643 mm. So that is 1650 mm. So at least 1/3 of the negative reinforcement, that is 1/3 of this reinforcement, should be extended to a distance 1650. So here we have the detailing diagram. Here we have the radial reinforcement, that is reinforcement is provided to a distance 1400. This is the greater of the three conditions as we have explained, and 1/3 of the reinforcement, total reinforcement, is provided to a distance 1650 as provided in the condition in the IS code. Okay, so even though there is no requirement of the circumferential reinforcement, here we are providing two rings of circumferential reinforcement in order to avoid slipping of these bars, radial bars. We are providing circumferential reinforcement, two rings. Okay, then this is the plan of top reinforcement. This is the plan of top reinforcement, that is here, because it is a tensile stress. Radial tensile stress is developed in the section. Since it is a fixed slab, there is a radial tensile stress at the top. Okay, so we are providing this radial reinforcement at the top, that is here it is represented in this figure. Okay, so there is bottom reinforcement, that we have already designed mutually perpendicular reinforcement, that is here it is given, that is bottom reinforcement 10 mm bars at 360 mm, that we have initially found out. Okay, so these are the reinforcement details. So apart from the simply supported slab, we have a radial reinforcement at the top in order to overcome the radial tensile stress at the top. So there is a negative moment developing because the radial moment at the edge has a value in case of fixed slab. Okay, so we are providing a radial negative reinforcement in this case, and this bottom reinforcement is same as that in case of simply supported slab. So this is the design of fixed circular slab.